Institute of Nuclear Chemistry and Technology presents a method of radiation sterilization of biological dressings and a package for transport and radiation sterilization of biological dressings. Skin is the largest organ in the human body. It has a protective function that maintains the body's homeostasis. Skin functions include various protecting, regulating, and sensing functions. Skin injuries, for example extensive burns or genetic diseases, may pose a direct threat and even lead to loss of life. In such situations, the only salvation is skin transplant. Allogenic tissue grafts, it is grafts collected and transplanted from the recipient, are a sought-after material for the reconstruction of the human body. A progress in skin substituting is the use of acellular dermal matrices, ADMs, which meet most clinical expectations and may serve as a dressing alone, or in combination with cellular therapy. One crucial element in the application of ADMs is their microbial sterility. Sterilization procedure aims to destroy and/or remove all contaminating microorganisms from a given material or product. Chemical methods of sterilization entail the use of chemicals that are hazardous to health and are not effective throughout the entire volume of the product, what is particularly dangerous in the case of materials with highly developed surfaces, such as those of natural origin. An alternative is a physical, radiation sterilization method. The application of ionizing radiation results in inducing the excitation of atoms and molecules in viral and microorganism contaminants. This triggers a chain of secondary biological reactions, causing damage to key intracellular structures and molecules. Currently, radiation sterilization is the recommended method as an effective way to ensure end product sterility in biologically derived materials and products. The advantages of radiation sterilization include the possibility of sterilizing objects already in sealed packaging, which eliminates the risk of secondary contaminations due to downstream packing. In addition, during radiation sterilization, no high temperature is required, with sterilization further able to be performed on dry ice to reduce the likelihood of product degradation. The choice of sterilization dose remains a critical parameter affecting final product structure and functionality. According to the International Atomic Energy Agency, the minimum dose for tissue sterilization should be not lower than 25 kilograms. However, to ensure the microbiological sterility of biomaterials, higher doses are often considered. Usually, a dose of 35 kilograms is considered sufficient to ensure septicity and maintain satisfactory product functionality. Electrons with kinetic energy up to 10 megaelectronvolts are routinely used to sterilize biomaterials. The graph presented here shows the dependence of the radiation dose in the irradiated material on the depth of the material with a given density. A typical electron beam depth dose curve has a dose buildup region. The dose buildup is produced by forward scattered electrons that stop at deeper depths of the material. As a result, as radiation passes through the material, the dose increases to values that can be up to 40% higher than the dose at the surface of the material. Maximum dose occurs at a certain depth referred to as the depth of dose maximum. Our invention exploits this property of high-energy electron beam that causes the buildup of the dose inside of the material. Acellular dermal matrices are thin layers comprised mostly of cellular collagen, and as such will be subjected to a uniform dose throughout the volume, even after one-side irradiation. To ensure that our sterilized material falls exactly within the dose maximum, we took advantage of the absorption of the radiation beam by a layer of dry ice, which also maintains a low temperature during irradiation, having a protective effect on the biological material. Biological dressing of human or animal origin is placed in a transport package having a two-part inner thermal insulating layer of polystyrene, filled with a 2 cm dry ice layer. The dressing placed in such a tight package is sterilized using an electron beam of the energy of 9.5 megaelectronvolts, with the dry ice layer faced towards the electron beam. The dimension and design of the package enhance the electron beam dose deposition. The parameters of the packaging were optimized and the dose distribution in the sterilization device was calculated and experimentally validated. The maximum number of allografts that can be placed in the sterilization device was determined. In effect, a sterilization dose of 35 kilograms is achieved in a mass corresponding to the cell-free skin matrix at an exposure dose of only 25 kilograms. This careful design allows an increase in the sterilization process rate by almost 1/3, which in a similar relation reduces the cost of the sterilization process. Thank you for your attention.